the other hour. Okay, here's what we did. I had this class fill these out. So input, say it, output. So they plugged in add values for x and then got the y's and then connected the dots. So here are those answers. If you want to do it, stop the video and then do these first four. Then I'm going to cover the fifth one, and then I'm going to go ahead and do the sixth one. So here's the first one. It's linear identity function. Plug in 1 for x, you get 1 for y. Plug in -1 for x, you get -1 for y. It's a line. So call it the identity function. You could call it linear. Second one is the absolute value function. It's because the absolute value of -1 is 1. Absolute negative of -2 is 2. Absolute value of 1 is 1. Absolute value of 2 is 2. You get a little v, a little bounce, a little vertex there. This is different than the next one, which is the quadratic. Let me move my fat head up. Yeah. Quadratic has curvature. 1 squared 1, 2 squared 4, -1 squared 1, -2 squared 4, -3 squared 9. This is curved, different than the previous one. Domain and range, though, the same. Increasing, decreasing intervals, the same. Chart of values there. Okay, then the next one, cubic, not the same as a quadratic, because -1 cubed is 1. Uh-oh. -2 cubed is -8. 1 cubed is 1, and then 2 cubed is 8. So those were the last one that I covered, and then we'll go into the square root here when the time is up. And that's it. Perfect timing. I did 2 minutes of a video there. You should definitely have this. Hey, what can't you take the square root of, class? Anyone? Huh? Negative. Well, you can. You'd get a decimal. Someone said 2, but that would give you a decimal, and you have to calculate it on your calculator. But negatives. What's the square root of 0? 0. What's the square root of 1? What's the square root of 2? I'm sorry. So he's right. What's the square root of 4 is what I meant to say. And what's the square root of 9? Those are the points you should have plugged in, and basically you only get this little curve. Did someone just clap for themselves? Nice. Okay, this looks like a half of a parabola. It is curved, and this goes forever. Because what's the square root of 16? Say it. 4. What's the square root of 25? Now, we're not ignoring, like he said, the square root of 2. That is actually a number. The square root of 2 is like 1.4. It would graph. That's why you connect the dots. These points are infinite. We just like to pick ones that are easy to get a sketch when we input output and make these figures. So now we do have for the first time in forever, we have a domain issue. We cannot plug in negatives. So that's where a domain is defined now as not all real numbers. There's a restriction. I can only start at 0 for x and then plug in a bunch of positives. And then the outputs, we got to, again, look at the y-axis and see how these are not covered down here. So the y-axis only has 0, and on all of these numbers, so 0 to infinity. There is 0, 0 again for an x and y intercept. Interesting. And it is only increasing. This is the parent. It's called the square root function. And now I'm just going to go ahead and go to the notes. That's why I started the video and actually do this. So I wanted you to practice that input output. I don't know why that screen is down there. Okay, got it. And go ahead and plug in some values. I'm going to need a bigger chart here. Now, here we go. This is great. Math 2 honors, you never saw this. Math 2 regular, probably never saw it. Math 3 regular, you definitely did. Mrs. Shavanik used to be in my room 2 years ago, and you guys were always up on the board. That wasn't you, the previous Math 3ers. And I'd see cubics all the time. So I would see the x cubed graphs, and then I would see these, which are called the reciprocal functions. I have a new pen, by the way. I'm very excited. And it's already not working. All right, there we go. Anyway, this is called, can everyone say reciprocal?
Reciprocal.
Did you hear him? You said it better. Reciprocal. I like saying that way so I can spell it right. They're actually called rational functions, though. And this is going to be a huge component coming up. This is going to be a big chapter. And so is cubics and actually polynomials, I should say, more than cubics. So we're going to do polynomials first, then we're going to do rational functions. Huge stuff. Blah, 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 blah. Okay, so let's plug in values. Well, this is easy. I guess I'll plug in like 1 here I'm going to have to extend this chart above there. But 1 over 1 is just 1. Okay, great. 1 comma 1. That doesn't do much. All right. Now you really got to focus on this and understand how this is happening and what's happening. Like, okay, what if I plug in 2? What happens when I plug in 2? What do I get as an output value?
1/2.
1/2. That's small. As a matter of fact, let's plug in 10. Let's get nuts. What does that become?
1/10.
Well, here's what we understand as humans. We understand that as I plug in big numbers, this is getting really small for output values. So we create this imaginary boundary line. We write this. It doesn't exist there, but we get annoyed. We don't want to have to keep plugging these in and show this behavior. This is going to happen forever. I plug in 100, I get 1 over 100, which is not, starts with a Z, not 0. As a matter of fact, this could never become 0. You could never get an output that is 0. That's why we draw that boundary line. This is called an asymptote. Sounds naughty. Can everyone say asymptote?
Yeah.
And this asymptote is actually y equals 0. Right? I'm going to write the word asymptote up above. Asymptote. This is a horizontal one. I'll move over. You're right. I'm kind of in the way, but I like getting the screen showing here as well. I'm weak today. I can't move this thing. All right. And it is y equals 0 because y equals is a horizontal line. But then you want to get nuts. Let's get nuts. What happens when I plug in a half? Why would I do that? Well, there's a bunch of points in between 0 and 1 I want to analyze. So if I plug in a half, what is 1 over a half? You make me sad if you don't know this. 2, because I've been teaching you about flipping. Okay, let's get crazy. What happens if I plug in 1/10? What is 1 over 1/10? Sorry, this is in the way. It's 10. So the idea is the closer I get to 0 on this side of the y-axis, these y values start going nuts, crazy up. As a matter of fact, 1/10 is even closer. Then here's 10 up here. So guess what else we have? Say the magic word again. There's a asymptote, and it's vertical. Maybe I like coloring the asymptotes a little bit different. They're hard to see with that big black line there. That's another asymptote. That is x equals 0. That's a vertical asymptote. Vertical lines are always x equals a number. And then I need another chart of values. I don't know why this isn't shrinking. Okay, I'm trying to shrink the screen. Oh, well. All right, and then I need my negatives. Well, let's start with -1. I get -1. Okay, so I'm down here. And then let's do that fraction thing. What's -1/2 plugged in? What do you end up getting? There we go, finally shrunk. What happens when I plug in -1/2 for x? What does that become? -2. And then what happens when I plug in -1/10? What do I get? -10. So what ends up happening on this end is this graph starts taking off straight down there. That's emulating those numbers I plugged in there. And then one more thing, -2 and -10. That becomes -1/2 and -1/10, which is getting closer and closer and closer to this asymptote on this side. So it kind of looks like two U's, but not really, not like a parabola. As a matter of fact, this is concave. What is this concavity? Concave what? Down, and this is concave what? Up. So it's very much, it's very similar to that. Now you got some major domain issues. I don't know why this isn't working. Okay, so the domain is everything, but I could not plug in 0 for x. I forgot to mention that. What happens when you plug in 0 for x? This is just not working. This becomes 1 over 0, which is undefined. But then I wanted to show not only, like someone asked me, I think I tried first hour to have them plug it in first instead of going over it. I might have done that both hours. You guys, I just went with it. And they asked me, what do I do when it's undefined there? I'm like, yes, you're right. It is undefined there. Here, I'll show you later. And it's that behavior I'm talking about as I get closer on both sides. So anyway, the range is the same as well, though, because I cannot get 0 as an output. I can't. It's impossible. You get very, very small for output values, but not never getting to 0. And then there is no intercepts. NA, you're gone. And then is it increasing or decreasing? What are both of these graphs doing? What are they both doing? It's actually, I shouldn't say both graphs, both parts of this one graph, because it is one graph. But anyway, you're right. It's decreasing. Unfortunately, I can't say from infinity to negative infinity. I have that interruption at 0, and the graph is not defined at 0. So I do have to split them up. Okay? All right, so Math 3 regular, you've seen this before. You actually did it a lot last year. Doesn't matter. You still need to see it. This is the harder, and this is why we're going to have a whole chapter on it again. And, it's probably going to be a complete reiteration of what you had last year. Believe me, I saw you guys on the board 2 years ago, or Math 3 students 2 years ago. Whatever the synopsis, I don't know what they want up there. I'm moving on. Okay, so which paired function demonstrates a constant, or functions a constant rate of change? Linear. Okay, but there might be one more, or it's called the what? What did we call the linear one? The identity function. Okay, but there's another one that at least parts of it does have a constant rate of change. Which one is it? If you take certain parts of it, what's the next one? Absolute value for sure. I keep doing that. I keep forgetting the absolute value in parts. So it's definitely, oh shoot, I'd have to go to because I didn't write them down. It's definitely, what's going on here? Okay. If I pick from 0 to infinity, any part in that interval, this has a positive linear rate of change. From negative infinity to 0, this has a negative linear rate of change. But if I say from -2 to like 4, well, then that's different. All right. So, you got to tread lightly on that one. I do want to mention it, though. There is some linear type behavior going on with an absolute value. So I would kind of put that in the mix. All right. So number 2. Which one is that from our parent functions? The last one. What do we call that? Reciprocal, or you could say rational, but I think they do call it the reciprocal functions. Let me hit the note key here and then go down to that. And called the reciprocal function. You can see it written over on the right. But really, they're called rational as well. We'll call it that when we get to it. What's the next one? Letter B. It's cubic. As a matter of fact, what you have in this one, and you Math 3ers, you remember this. In Math 2 honors, we're going to do the polynomial dance tomorrow. Remember that? Who was in my? Remember that? Okay. X cubed, negative x cubed, x to the fourth, negative x to the fourth, and then in homecoming you'll see people going crazy doing the polynomial dance on the dance floor. Yes, you will. Okay, but unfortunately for this one, not unfortunately, there is a little bit extra character in there. The x squared and the -1 might give a little bit more loopage in there, more roller coaster activity. But really, it's just the cubic is all we need. And then what's the last one? Come on. Abs veil. All right. Okay. Now, this is back to the things that we have already done, and this is going to get bigger and bigger. You're going to get coordinate values, like just on a chart, and you're going to have to maybe pick what it is. Okay, at least they don't have any of the others. It's back to our question from the test. Linear, quadratic, or neither. Okay. First thing I better check that the x's do go up in equal input intervals. And this is going up to, so that's good. So if I were going to determine what's the slope of this, I'd have to do change in y over change in x. It'd have to be divided by 2. But when I look at the y's, these go down 2, and then they go down 4. Is this linear? Yes or no? Is this linear? Yes or no? No. Down and then down 8s. But I could see a pattern there. So is this quadratic? Yes. Okay. So actually, the first order differences would actually be half that, right? Because these are by 2 over here. But you're okay. I just need to see, is there a pattern from here to here? And then this is down 2, down 2, down 2. Is this quadratic? Yes or no? Yes. What's its concavity? That's an added thing.
Concave down.
Concave down. So this is going down. This is quadratic. And then just for giggles, you can put that it's concave down. Because that's stuff we've already determined from before. Then this is where this gets a little tricky. They get a little jerky because this goes from 0.5 to 1. So that's up 0.5. But then 1 to 2 is up 1. That's not an equal set of interval values, input intervals. But then it does go 0.5, and then it does go 0.5. So I'm going to analyze going up 0.5, do I have the same slope values? So from 0.5 to 1, this goes up 8. And then from 2 to 2.5, this goes up 6. Is it linear? No. And then 2.5 to 3 is up 0.5, and that's up another 6. That's weird. I went up 0.5 in one set of intervals, and it was an 8 difference for y. Then the other two are 6s. Is this quadratic? No, because there's not like a common pattern there after the next one. From 6 to 6, that's a common difference of 0. And then looking at this one from 1 to 2, which is a full unit for x, this goes up 16. You could divide that by 2 to get what it would be by halves, like 1 to 1.5 and then 1.5 to 2. But still, 8, 8, 6, 6. If I took those differences, I would not have a common second order difference. So this is a neither. A little bit trickier on that scenario. This only works for polynomials. This first, second, and then you're going to find out for cubics, third order differences. Quartics, which is x to the fourth, is fourth order equal differences. So on and so on and so forth. Gets nuts. All right, and then I'm skipping this one. I know what they wanted, but I just don't think it fits here, and it doesn't really apply to what we're doing right now. Just analyzing and recognizing. Okay, but this is just function notation that we should be able to figure out. Okay, so when you read it, let f be the absolute value function. Well, write that down. If f is the absolute value function, then f of x equals the absolute value of x. It's that parent. Notice my pen's writing great. I got a new pen. Very excited. G being the cubing function, sorry. So g of x equals the cubing function. Oh, sorry. That wasn't the pen. That was my brain short-circuited for a second.
It's a tough
All right.
G.
Huh?
It's tough G.
So now find 2f of -3 plus g of -1. Well, everyone knows what g of -1 is. G of -1 means plug in -1 into the g function. And then I have to add that to, wait a minute, well, f of -3, that's easy. That means I go to the f function and I plug in -3. What's that 2 out in front mean? 2 times. That's it. So that's all this means in function notation, the ability to evaluate. And then order of operations, please. You do parentheses first, which is those, absolute values are like parentheses. So that's 3. And then 2 times that. And then do parentheses or exponents. Better way of saying it is exponents. And that -1 cubed is -1. So 6, now you multiply, and then you subtract or add, and you get 5. So you just get a number as a final answer. Okay, so just a weird little function notation question that is expected to know, you know what to do with that. All right, that should be good for the notes. The homework should take no time whatsoever.